Assalamualaikum and good day to Dr. Shakina. Today, our group is going to present the first ordinary differential equation application project. So here are the members of our group, Group 7. First is myself, Aizzudin Azeem, Yap Jia Nie, Ealvina, Rifqah, and Nurul Qurratulaini Najwa. Next, the project introduction. This project is related to the energy balance project. The objective of this project is to apply the first differential equation in a daily life problem. In our context, as chemical engineers, we use this knowledge to solve the problem for our plant design. As for energy balance project, we were assigned to produce 550,000 tons of ammonia with coal as our feedstock. So in the process of ammonia production, there are many situations where specific temperature and pressure are needed to make sure our chemical reactions take place. Hence, this is why we need to do the calculation in order to gain our favored temperature and pressure. And this is where we apply our first differential equation. So for our project, the equipment selected is heater, a unit that is used to increase the temperature of its components. The heater is used to heat up methane and other elements needed for ammonia production like nitrogen. So the two methods that we chose is the first one, variation parameter, a general method to solve inhomogeneous linear ordinary differential equations. So this method can be used for finding a particular solution of a differential equation by replacing the constants in the solution of a related equation by functions and determining these functions that so that the original differential equation can be satisfied. The second method that is chosen is integrating factor, a commonly used method to solve ordinary differential equations by using a function. So an integrating factor is a function by which an ordinary differential equation can be multiplied in order to make it integratable. So this is our unit heater, and in our project, heater is used to increase the temperature of oxygen and nitrogen from 25 degrees Celsius to 450 degrees Celsius.
My name is Yap Jia Nie, matrix number 207158. So to solve the problem for our heater, the first method we use is variation parameter. So this is a Newton law of heating equation. dT over small dt equals to K T minus initial temperature T. So the first step is we have to rearrange the Newton's law of heating equation. So dt equals to K T minus T naught. Then we rearrange into 1 over T minus T naught dt equals to K dt. We switch the position of the equation to get this. So we rearrange them. So the next step, step 2, we integrate both sides to form separable variable. Integrate both sides. Integrate this 1 over T minus T naught dt and we integrate K dt. When we integrate 1 over T minus T naught, we get ln. This is 1 over, so ln T minus T naught equals to KT plus C. Then after that we use exponent to make the ln disappear, so it will be T minus T naught equals to CE KT to the power of KT, exponent power of KT. So step 3, made some assumptions. For the case 1, the heater took 9 hours to carry out heating process from 55 degrees Celsius to 450 degrees Celsius. And then for case 2, the heater took 5 hours to carry out heating process from 55 degrees Celsius to 250 degrees Celsius. Next step, step 4, we substitute the equation based on the assumption we have. So T minus, initially it was T naught, so the room initial temperature. So T minus 55 equals to CEKT. Then we e to the power of KT, exponent KT. Then later we rearrange, make T the subject title, is to C e to the power of KT plus 55. So from the assumption, the case 1 and case 2, case 1 we get T9 equals to 450. 9 is the 9 hours to reach 450 degrees Celsius from 55. Then T5 is the case 2, which it takes 5 hours to reach 250 degrees Celsius. Okay, so the next step, step 5, substitute case 1 and case 2 to the separable equation. So just now T, we substitute T with 450 temperature equals to T0, the initial temperature, 55, plus CE to the power of 9K. Initially it was KT, so that's T stands for the time, small letter t. So it took 9 hours, so we substitute 9K. Later we make CE 9 to the power of 9K the subject title, and then we get 395. And for the second case, 250 degrees Celsius, then 55 is the initial temperature, CE to the power of 5K. So 5 is 5 hours. So we will get the second equation, CE 5K equals to 195. So equation 1 and equation 2 from case 1 and case 2 respectively. So we move on to the next step, step 6. We divide equation 1 by equation 2. So 395 and CE to the power of 9K is from equation 1 divided by 195 CE power of 5K from equation 2. So we will get E 4K, E to the power of 4K equals to 2.0256. Then we find out the value of K equals to 0.1765. Then for step 7, we substitute K into equation 1. So this is the equation from equation 1 previously. So we just substitute the value of K that we found previously in the equation. And we will get C equals to 80.69. Is the value of constant. Move on to step 8. The linear form of first ODE can be. So this is the Newton law of heating. Capital T over dt. So KT minus T0. Then we sub the initial temperature into the equation T0 55. And later we sub the value of K that we found previously 0.1765. Later we times into the bracket, so we get 0.1765 T minus 9.7075. Then we rearrange it into the form of a linear form of first ODE, so dt over dt plus fx equals to rx. So dt, so we get dt over dt minus 0.1765 t equals to 9.7075. So from this linear ODE, first ODE, we get that ft equals to negative 0.1765, or rt equals to negative 9.7075. So that's all from me. I will pass the next step to groupmate Ealvina. Thank you.
My name is Ealvina with matrix number 206611. Step 9, which is to change to homogeneous linear by letting RT is equals to 0. dt over dt minus 0.1765t will be equals to 0 since we are letting RT is equals to 0. So we move it to the left hand side. So dt over dt will be equals to 0.1765t. So in order to get our temperature, we have to integrate the equation. So after integrating, we will get T is equals to e to the power of 0.1765t. Moving on to step 10, which is to obtain as a particular solution. So by using the equation that we've gotten from step 9, we will times it with Bt. So temperature will be then equal to e to the power of 1765 T times Vt, and this will be our equation A. Step 11 is to differentiate it by using chain rule or product rule. So now we have to use chain rule to differentiate the equation, which is equation A. Now we are letting u equal to e to the power of 0.1765t, and then differentiating u in terms of du of dt, we will get 0.1765 times e to the power of 0.1765t. And then the other part, which is Vt, we will let it be V. And then by differentiating it, we will get V prime. And then by using chain rule, which is uv prime plus vu prime, we will get our equation B. So dt over dt will equals to e to the power of 0.1765t times v prime plus vt times 0.1765 e to the power of 0.1765t. And this will be our equation B. Step 12 is to substitute equation A and B into equation of linear form of ODE. So just now equation A and B, we will substitute it back to the equation of ODE, which is at step 8, dt over dt minus 0.1765t equals to negative 9.7075. So dt over dt will be our equation B, and then t will be our equation A. And then after that, we can see that this cancel off, and then e to the power of 0.1765t times v prime will be equals to negative 9.7075. And then in order to get vt, we have to integrate it. So after integrating the equation here, we will get 1.7134 divided by e to the power of 0.1765t plus c. Okay, step 13 is to substitute vt into the equation A. So just now we've gotten our vt, so then we can substitute it back to the equation A. So after substituting it to vt into equation A, we will get t is equals to 1.7134 plus c times e to the power of 0.1765t. Now since we've gotten our equation, all we have to do now is to find the value of c, and then we will get our particular solution. Step 14 is to find the value of c, and you use the case 1 of the assumption. So here we are using case 1 of the assumption, which is T5, time is equals to 5, temperature is equals to 250. So substituting the values into the equation that we've gotten from step 13, we will get our C, which is 102.7279. Step 15. Now, since we've gotten our C value, just substitute it back to the equation, and then we will get temperature is equals to 1.7134 plus 102.7279 e to the power of 0.1765t. So moving on to the application question. The question is, what is the temperature of nitrogen gas when the heater carries out the heating process for 3 hours and 15 minutes? We have to find the temperature where the heating process is carried out for 3 hours and 15 minutes. So our time will be 3.25, and then now we have to find our temperature. By substituting our time, which is 3.25, into the equation, which is our particular solution, we can get our temperature. Temperature will be equals to 184.023 degrees Celsius. Thus, the temperature of nitrogen in the heater after 3 hours and 15 minutes is 184.023 degrees Celsius.
Method 2, integrating factor. So we know that the Newton's law of heating equation is change in temperature over change in time equal to K times temperature minus initial temperature. So we transform the Newton's law equation into the general form of first order linear ODE. We get change in temperature over change in time minus K temperature equal to minus K initial temperature. So we know that F equal to negative K and R equal to negative K T naught. So step 2, find the integral F dt. So we get negative K T. Step 3, integrating factor IF. So IF equal to e to the power of the integral F dt. We get e to the power of negative KT. Step 4, we need to find the general solution by using this equation. So we substitute the value of IF and R into this equation. So we can get the general solution is T equal to initial temperature plus CE to the power of KT. So we substitute the initial temperature equal to 55 into the general solution in the step 4. We get temperature equal to 55 plus CE to the power of KT.
Okay, now let's move on to step 6. So we need to do assumption. So we have two assumptions here. For case 1 is the heater took 9 hours to carry out heating process from 55 degrees Celsius to 450 degrees Celsius. And for the case 2, we have the heater took 5 hours to carry out the heating process from 55 degrees Celsius to 250 degrees Celsius. Okay, for step 7, we need to substitute case 1 and case 2 into equation in step 5. For case 1, t is equal to 450 and the small t is equal to 9. Substitute it into the equation in step 5 and we will get 395 equal to c exponent 9k and label it as equation 1. For case 2, t is equal to 250 and small t is equal to 5. Substitute it into equation and we will get 195 equal to c exponent 5k, label it as equation 2. Moving on, we need to divide equation 1 by equation 2. So after we divide equation 1 by equation 2, we will get the value of k. So the value of k is equal to 0.176. Next, we need to substitute the value that we get just now into equation 1. So the value of k is equal to 0.176 and then substitute into equation 1, we will get the value of c. So the value c is equal to 81.04. Okay, for the last step, we need to find the particular solution. Since we already know the value of k and c, we can substitute it into equation in step 5. And then we will get t is equal to 55 plus 81.04 exponent 0.176t. Okay, the application of problem arises and its solution. So the question is, what is the temperature of nitrogen gas when the heater carries out the heating process for 3 hours and 15 minutes? So the question is already given as time, which is 3 hours and 15 minutes, and it's equivalent to 3.25 hours. So we can substitute it into the equation that we get just now, which is t is equal to 55 plus 81.04 exponent 0.176t. And then we can get the value of t, which is 198.59 degrees Celsius. So the temperature of nitrogen gas after 3 hours and 15 minutes is 188.59 degrees Celsius.